All right, so let's continue on with functions. All right, so in the previous video we talked about what a function is and graphically or visually what is required for a relation to be a function, and that is it must pass the vertical line test. So as I indicated in the previous video, all of those relations we saw, so all of them were relations, but only some of them were functions. So to summarize, all functions are relations. Okay, they're special. But not all relations are functions. So as we saw previously, the circle, okay, that's a relation, but it's not a function. So all functions are relations, but not all relations are functions. Okay, so here's an example here. Both of these are relations, okay, but which one is a function? Well, which one passes the vertical line test? So if my pencil was here, 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 no matter where, it only touches my graph once, so that's a function. But here, I'm always crossing twice, okay? So that is not a function, okay? Well, this analogy, you can actually extend that outside mathematics. So let's have some fun with it. So look at a hand. All thumbs are fingers. It's a type of finger. All thumbs are fingers, but of course, not all fingers are thumbs. Okay. And there's actually another example that I like to use. Believe it or not, some people don't know this. That's why I want to throw it in. Here I have a square and I have a rectangle. But believe it or not, I actually have two rectangles. All right, so a square, it is a rectangle. It's just a special kind. So all squares are rectangles. But of course, not all rectangles are squares. So you can think of these two as half-decent analogies of a function versus just a plain relation. Squares. All right, it says graph each relation below, determine if it is linear, and then use interval notation to describe the domain and range. That's at the bottom. All right. I don't specify it here, but I'm also going to make note of which of these relations are functions and which ones aren't, since we're on that topic anyway. So here we have a relation, and we actually already know that this is linear just by looking at the algebra. Okay, remember we can look at the exponents attached to the variable. Okay, so I actually already know, but it says to graph it, so by the next chapter, you'll be able to look at an equation like this and just graph it right away. But let's use a table of values just for now. So you can choose any number input value for x. So 2 times 0 is 0. Take away 3, well, that's just negative 3. So that is an ordered pair, so I can plot that right there. There we go. All right, let's choose, I don't know, x equals 4. Doesn't matter. All right, 2 times 4, of course, is 8. 8 minus 3 is 5. So that's another ordered pair. I'm following this rule. So 4, 5, right there. Okay. And the next one I'll choose, I don't know, 6. 2 times 6 is 12, and 12 minus 3 is 9. So I'll plot that one. That's 6. There we go. Just like that. Okay. Well, I think it's clear from the picture that it is linear. And we are allowed to connect these dots, because I just chose these at random, but I could have chosen any dot I wanted, or any x-coordinate, and it would have plotted a dot anywhere along this straight line, which I'm about to draw. So get that going. something like that. Enough. Because this is a line, not a line segment, put these arrows here. Okay. So it is definitely linear. And now it wanted the domain and range, but it wanted it in interval notation. Well, it goes on forever. So it goes to the right forever. Remember, domain is horizontal. And it goes to the left forever. So it goes left all the way to negative infinity and right all the way to positive infinity. And whenever we use infinity, these are always rounded. Okay. What's the range? Okay. Again, the range is just up, down. It's just vertical. Well, the graph clearly goes down forever, and it goes up forever. Okay. So there's our interval notation. And let's just make note, is this a function? Does this pass the vertical line test? Yes. If I was to draw or put my pencil here, it would only touch this relation only once. So every x value produces one unique y value. So I will put right up here, function. There we go. All right, so for the next relation, we have y equals the square root of x. So it means whatever number we choose x to be, we take the square root of it, and that becomes our y value. Well, I can tell you already this is not going to be linear, but let's create a table of values and you'll see why. All right. So because we're not using any calculators, we want to pick numbers that are easy to work with. Okay. So if you were to pick, let's say x is equal to 7, and you try and take the square root of that without a calculator, good luck. Okay, maybe by trial and error you can get a few decimals, but that is very painful, and we just don't do that anymore. So let's pick some simple numbers. Let's pick, well, 0. Okay, so what's the square root of 0? Okay, meaning what number times itself would give me 0? Well, that'd be 0. 0 times 0, so there we go. So that's a point that I can plot. And there it is. Can I allow x to be negative? Okay. Well, can you take the square root of a negative number? Well, take your calculator just for fun. Try it out. You'll get an error message every time. Okay. Right? You can't take the square root of negative numbers. I'll never ask you to. Well, another nice number would be 1. Why? Because we can take the square root of 1. What number times itself is 1? That's just 1. So I can plot that there. 1, 1. Okay. So now we have to start being a little bit more careful. You might think, well, I should just choose x is equal to 2. But that wouldn't be a good idea, because the square root of 2, that is an irrational number. Remember, we talked about that. That on a calculator would be 1.4 blah, 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 and it goes on forever, and it doesn't repeat. Right? So let's pick the next x value that would give us a nice answer. Well, I believe that's 4. Because the square root of 4 is 2. Okay? So I can plot that. 4, 2. There we go. So you can see already it's not linear. All right? And I think we'll plot one more, because I believe that's all the room I have. Okay? X equals 5, x equals 6, x equals 7, x equals 8. None of those would be wise choices, because the square roots of those numbers are not particularly nice. They're irrational numbers. But 9, however, that's nice. Okay? What number times itself is 9? Well, 3 times 3 is 9, so therefore the square root of 9 is 3. Okay? So let's plot this. X is 9, y is 3. That's 10, 9, there we go. And there we go. And we could have of course, go on and on. So I'm going to connect these as best I can. So graph would look like that. It would go on forever. But clearly it's not linear. Okay? All right. So what is the domain? What is the range? And we want interval notation. So again, domain, we're only concerned about x values. So forget about these y values. Well, x equal to 0. 0 is the lowest we can go. Okay, we can't choose negative values because we're not allowed to choose, we can't take the square root of a negative number. Okay, so this is as far left as we can go. So the domain includes 0, so that's a square bracket. Okay, but there's no limit to how far to the right this graph goes. It goes forever. So it goes to positive infinity. So therefore this is automatically round. All right, what's the range? So we're talking vertical. How far down does it go? How far up does it go? Well, the lowest point it reaches is y is equal to 0. That's included, so that is 0. And of course, yes, the graph goes to the right, but we don't care about that. Notice it is also still going up, albeit very gradually, but it does continue going up forever. So it also goes to infinity, which of course makes that round. Okay, is this a function? Well, we know it's not linear, but yes it is. Because if you try your vertical line test, it will pass. I guess I better circle this here, I forgot. Nonlinear, there we go. All right, last example, it's very similar to the previous one, but we have a funny little symbol in front of here. That means plus or minus. So we're actually given two different options. So if I was to create a table of values, we're still taking the square root, but with my answer I'm able to choose the positive or the negative. If I choose x is equal to 0, okay, y would be plus or minus 0. Well, negative 0 is still 0, so that makes no difference. So I'll still plot that here. There we go. But when x equals 1, okay, well we know that the square root of 1 is 1. But we're going to allow positive 1 or negative 1. So notice how for one x value, I'm getting two possible y values. Okay, right now you should be thinking, uh-oh, something's funny going on. So x is 1, y could be 1, or negative 1. If you've been paying attention, you'd know already that this cannot be a function. Let's complete it. So choosing the same values as before, x is 4, the square root of 4 is 2, but we're allowed to do plus or minus according to what this equation says. So if I plot these, I have two different choices. X is 4, y could either be 2, or it could be negative 2. And then 9, this would be 3 or negative 3. So plotting this would be 9, 3, or 9 comma negative 3. And you'll notice that really all we have is this relation, which is also a function, but it's like it's reflected, it's flipped. So let's connect them. As best I can. Something like that. Okay, so it's a perfectly valid relation, but of course, that's not a function. It's definitely nonlinear. Okay. So I'll just put that up here right now. It's not a function. Definitely not. Whoop, run out of space. All right, so looking at the domain, so horizontally, the graph goes as far left as 0 and goes as far right as, well, to positive infinity. So it's the same as the previous one. It should be round. But the range is different, okay? Because we have both of these pieces, the graph not only extends up indefinitely, it also goes down forever as well. So the range actually could be anything. So it could be as far negative as negative infinity or as far positive as positive infinity. There we go. So notice the difference between the two.